Okay, all right. We're going to pick up where we left off. I used the wrong kind of marker. Oh, no. This is now an advertisement for it. This lecture was brought to you by. I don't know what we're going to do with this.
I heard that if you use your erasable marker,
Yeah,
you
if you
just
use a regular expo marker and
Right.
color over it, but it has to be pretty soon afterwards.
right, and then you erase it immediately after. You just write over it like scribble.
Alcohol.
Can we just do the spray thing?
Yeah.
The sprays? I don't know if there's one in that department.
Does hand sanitizer work?
Yeah, I don't know. Oh wait, I think this is working. Didn't take forever, but.
Do you want hand sanitizer?
Hand sanitizer?
And tissue?
There we go.
Introducing the eraser. Like it's just, so all our sponsors include. You need to like speed up the frames now. Play some weird music in the background.
Want hand
I
sanitizer?
think you
Does anyone have hand sanitizer?
Right here.
Can bring it up.
Yeah, sure.
Let's see. Oh, we have tissue. Thank you. We also have, it's really QVC, that's what we are. It's not like. After this, I mean, I'm too tired. Just let's go home. Just, this is not working out. Today on Mythbusters, is alcohol better than using a marker? It turns out we busted that myth. This actually works a little better. It's crazy. I don't even think it's a chemical thing. It's like sheer pressure that I'm just getting rid of all these molecules on the board. But they left their name, so I'm going to look this person up.
Oh God, it made it worse. Oh, that's gone.
I mean, it's workable. Okay, so today,
Why is my OCD kicking in?
all these alcohol companies now are going to have like a drop in sales, so like 50% of our customer base was using us to get rid of permanent marker. Damn you, Javon. Now they know the truth. Who's using
That's his.
Thank you. Okay, so now we can start. We're going to recall about span, which I think I mentioned that in a specific context, but I want to give a bigger definition now. The thing is, it's more of a vocabulary word, so you can sort of use it in many ways, but I just want to make sure that we have. And I did give you that theory before. So let V be a vector space and S be a set of vectors where all the VI's are in V. Then we saw that W equals the set of all possible linear combinations, like A1, B1 plus A2, B2 plus A and B n, such that your AI are real numbers, they're scalars, is a subspace of V. Right? It's closed under addition and scalar multiplication. Now for some terminology, we say W is the space generated by S. We can also say S spans W. Is that the direction I want to go in? Every vector here is a linear combination of vectors in there. Or, let me say it differently. We can also say that the vectors B1, Bn span W. Yeah, so S spans W. That would be a phrase that we can use. I.e. Say the vectors span a set. Multiple terminologies. I wanted to see which one I want to say. If every vector in V can be written as a linear combination of vectors in S, we can say S spans. We talk about spanning a vector space, spanning a subspace. Basically, we say U spans V if every vector in V can be expressed as a linear combination of vectors in U. So let me give you a concrete example. If I look at this set, the vector is 1, 0 and 0, 1. I can say this spans R2. Why? Take any vector in R2. So I call it A, B in R2. We can write AB is equal to A times 1, 0 plus B times 0, 1. The fact that I can write this vector as a linear combination of these two means that it spans this space. Right? And that would work for any vector. So span is sort of a linear combination kind of language. So we say, if I can write any vector in here as a linear combination of vectors in here, I say this spans that. Okay? And I want to do some more examples here. Oh, another notation here. We may write W equals the span S, or W equals the span, and I can write the set B1 to Bn. So that's also a notation. So this is saying every vector in W can be expressed as linear combinations of vectors in S. I gave you another example, one example. Let's do some more examples. So let's talk about in Rn. This is language that I'll explain later, but this is called the standard basis, is given by the set E1, E2, all the way up to En, where EI equals the matrix of all zeros except there's a 1 in the ith position. So you can say E1 is just there's a 1 in the first position and zeros everywhere else. E2 is there's a 1 in the second position and zeros everywhere else, and so on. That language I'll explain later, but for now what you need to know is that the set S equals E1 up to En spans R3, Rn. So another example, again, in R2, we have that E1 is just the I vector, while E2 is the J vector. In R3, E1 is I, E2 is the J vector, and E3 is the K vector. And these have the definitions you're familiar with. So this is the vector 1 comma 0 and the vector 0 comma 1, and this is the vector 1 comma 0 comma 0. This is 0 comma 1 comma 0, 0 comma 0 comma 1. But this idea extends in general. So for higher dimensions, we don't use IJK anymore. We use E1, E2, E3, E4. So that's a very important example. So the EIs are called the standard basis vectors. I'll just leave it at that. Just know that vectors like these will always span Rn. We'll talk about bases more later on. Another example is with polynomials. Remember, Pn is just the set of all polynomials. Of degree less than or equal to n. Then S equals these guys, 1 x squared, all the way to xn, form the standard basis. I can write any polynomial as a linear combination of these guys. Okay. So this is the standard, basis. Since any polynomial it spans Pn, since any polynomial can be written as I can write as a linear, a polynomial is really just a linear combination of powers of x. So just some different language here. Let's actually do something more computational. It's going to be important later. Determine if the following span R3. So here I'm going to give you 3 sets. S1. Let it be these vectors. 1, 2, 1, 0, 1, 1.
Is that the power set? Oh,
No. Power set is something very different. B, S2 minus 1, minus 2, comma 2, 1, 1, comma 0, 0, 1. C, S3 equal 1, comma 0, comma minus 1, comma 0, 3. So we say a set of vectors span a space if every vector in that space can be written as a linear combination of the vectors in the set. And so if I want to know if a set of vectors span R3, what I need to prove is that if I pick any random vector in R3, I can write it as a linear combination of these vectors. Actually go with A. So given that I told you that, how do you think we'd go about determining that? Yeah?
Determine if you can make the standard basis out of the vectors, like basically by
No, standard basis only refers to
Okay.
the definition as I mentioned. So this is some other thing, right? Some other set. I want to know, is it a spanning set? We'll talk about bases later because you don't just have to span to be a basis. You need another thing. How would I check that if this set spans R? What does it mean to span R? R3. What do we need to check?
Set of all polynomials of degree n.
No, R3, not P3. All three-dimensional vectors. What do we need to check?
You need to make sure that you could get to any number in R3, any coordinate in the three-dimensional.
Okay, so call the coordinate something, right? So call it, I don't want to use XYZ because people tend to refer to that as a variable. Let's call it ABC. We need to check that any ABC in R3 can be written as, well, check whether. Can be written as, can I take any random vector and write it as a linear combination of this guy? A3. Yeah?
Okay, the strategy that I was thinking of was, can you, if you turn that into a 3x3 matrix, can you make the identity matrix out of it? Because then if you could do that,
Which, turn what into that?
those three vectors.
So we would start by like adding, you're saying a bunch,
Yeah, like if you
combine to one big thing and write it as a matrix?
and write it as a matrix, and if
Okay.
you can use type 3 row operations to make the identity matrix out of it, then you can combine them in a way that you could get to any value in R3.
Okay, but that's what we want to see, right? So basically what is this saying? If I add all the first components, what would I get? A1 plus 0 plus, well, minus A3, right? If I add all the second components, I get 2A1 plus A2 plus 0. If I add all the third components, I would get A1 plus A2 plus A3, right? And what I need to check now, is it true that I can say A1 minus A3 should give me A, because that's the first component, they have to be equal. So I said corresponding components equal. 2A1 plus A2, can I get B from that? And can I get A1 plus A2 plus A3 to be equal to C? And what is that? That's a system of equations. So now we need to figure out, does this have a solution, in other words? Right? So in other words, does this system, does this guy where this is 1, 0, minus 1, 2, 1, 0, 1, 1, 1, have a solution. Okay? So it ends up, this question of asking whether or not something spans something else ends up being a question of, does this system of equations have a solution? Now, what are some ideas that you might say? Ideas. How would I know if this system has a solution? This will have a solution if, is there anything that can guarantee that I can find a solution?
Determinant.
You can talk about the determinant. So if I call this big matrix here A, I can say, I know there will be a solution if the determinant of A is not 0. That's one thing I can say. But that forces me into a box, doesn't it? What would that mean? The determinant is not 0.
There are no 0 rows or columns.
Sure, but in terms of solutions, what would that mean?
Unique solution.
Huh?
Unique solution.
Would it be a unique solution? So me checking about determinant can only tell me if there's a unique solution. Here I'm not really worried about is the solution unique. Here I just want to find any solution. So it is possible for the determinant to be 0 and still I would have some sort of solution. So for now, let's actually just do it the long way and do row reduction. Right? This will only talk about unique solutions. Pretty soon I'm going to justify you to that the unique solution is actually the one we care about, and in the case where there are infinite solutions, we actually don't want that anyway. But for now, let's talk about finding solutions. So let's go a little bit more general than that. Let's do row reduction to kind of see what our solution looks like, what are our properties, are there an infinite number of solutions? That would be possible. So basically what I'm going to do is I'm going to augment this guy with A, B, C, and I'm going to do row reduction. Now, row reduction is test 1. I'm not actually going to go through that with you. I would assume that you all know how to do that. I actually wrote down the shortcuts. It turns out that this guy actually reduces to 1, 0, minus 1, 0, 1, 2, 0, 0, 0, 0, 0, 1. Okay, so what can you tell me about that?
Inconsistent.
Huh?
It's inconsistent.
It's inconsistent. So if I just went determinant at this point, and I figured out, I would have gotten the determinant was 0, right? And I wouldn't really know, does that mean there's no solution or infinitely many? But at this point, by doing the row reduction, I can tell that it's actually inconsistent. So what can I say then? S1, how?
Does not span.
Does not span R. Not span R3. This means there is at least one vector in R3 that cannot be written as a linear combination of these guys. there is at least for emphasis. You had a question?
Yeah, in the final column of all the matrix, where do we get 0, 0, 1 from?
Oh, I did the row reduction. I just skipped the steps. I found the reduced row echelon form. I just skipped the steps. All right, so I did that whole thing where, oh, this is a pivot, kill everyone below that, so
Yeah,
multiply row 2 by blah, 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 and add them together. I do a bunch of operations, and I'm just telling you the result, because I would assume we all know what would happen between these dots at this point. I just want to save time and just tell you. This is what, if you went through the find RREF, this is where you would have ended up. Okay? But that tells me here, the last row tells me, that means it's inconsistent.
Professor,
Yes?
how did you get a 1 value? What's the if C does not equal E minus A?
Yeah, I get this under this assumption.
Okay.
And if C was equal to B minus A, it was actually consistent.
Okay.
So that tells me that it works for some.
There's some.
It actually reduced to the identity matrix. If this. So in the event that I restrict my C value to be B minus A, it would reduce to that. There comes a point here where you have to make a choice. Okay, pretend this or not, and then it worked out to this. But the fact is, there is a set of vectors for which it's inconsistent. I can't actually solve it for those sets of vectors. So in other words, the set of all linear combinations of this guy is definitely a vector space, but it's just not the entire vector space. It's a subspace. There will be some vectors for which it works and some for which it doesn't. What about P? Look at S2. What was S2? Now I'm gonna slightly change the notation here. It's gonna be easier to do. Yeah.
Do you know the vector ABC?
No, I need to show that it works for any vector ABC. So I don't want to pick a particular
So
one.
if you reduce that, how do you get numbers that are ABC?
You get 1.
What?
Like
How do you get 1?
if you're trying to reduce the matrix, how did you get?
Go home and do it.
No, but if you do an operation on that,
You end
on
up
any
with,
row.
you end up with things like A minus A and B minus B.
Oh,
Yes.
okay.
Oh.
And at some point, I make this choice, and if you go home and do it, you'll see. I want to save time. The row reduction is not the main point of this lesson. The point is to show you the idea that doing this check amounts to solving a system of equations. I expect you to know how to solve a system of equations. That would have been where you ended up. Okay. If we look at S2, and at this point, I'm going to change the notation slightly because it's going to be very suggestive. And instead of writing the vectors horizontally, I'm going to write them vertically, just like how we did in the solutions when we were solving systems. And you'll sort of see why when I do it now. So it was 1 minus 1 and 2 minus 2. It was 0, 1, 1. Oh no, it was 2. And then it was 0, 0, 1. Right? And why I kind of write it vertically is because now you won't have to go through all these steps. You can kind of see how things are going to plug in. What I would do is I would take A1 times this plus A2 times that plus A3 times that, right? And then notice that the A1 is just the first component. The A2 will tell you about the second component. And what's going to happen is you'll notice that the vector here, the horizontal vector, it kind of ends up being the vertical vector here. And the horizontal vector here kind of ends up being the vertical vector, and so on and so forth. So writing it in a vertical way in general sort of allows you to skip to the system that you want to solve. So you're literally going to put those vectors right beside each other. Set that equal to A, B, C, and ask, does this have a solution? So we'll go through, and it turns out that this one does sort of have an expected think.
Question, sorry.
Expected. I'll need more space here. So when I reduce this one, again, I do row operations to break it down. And that one actually reduced to, there was the identity on this side, 1, 0, 0, 0, 1, 0, 0, 0, 1, which first of all means there is a solution. In fact, it's going to be unique, and it's going to be this guy. A minus 2b all over 3 will give you a plus b all over 3. And down here we'll give you a minus 5b plus 3c all over 3.
Question.
Yes?
The S2, those elements, PDU is another set of samples?
It's another set.
Okay.
It's another example, another
Yes,
question.
all right.
So in A, we were checking about these 3 vectors.
Okay.
It turns out that they don't solve that equation, which means they don't span R3. In S2, I'm looking now at these 3 sets of equations. They end up being setting up, I end up having to set up this system to check for span, and it turns out that it does have a solution. So you give me any random vector in R3, I can express it as this times the first vector, that times the second vector, and that times the third vector.
And, Professor, so if given, if given a vector in R3, you
Yeah,
can
so
plug the
for
values-
example,
yeah.
Take, what vector do you want? 1, 2, 3?
Sure.
In R3. This would mean that your A is 1, your B is 2, and your C is 3. And so the system that I just computed would end up looking like this, where my A is 1, my B is 2, so that would be what? Minus 1? Right?
1/3.
What?
1 minus.
I plug in 1,
Oh.
minus 4,
Yeah.
minus 3 divided by 3 is minus 1. Reminds me of an ex-KCD comic. It's like, it's crazy. Like you go to calculus 3 and you have to explain the algebra. Like, what do you mean? How did I get that? It's just. So yeah, like yeah, we're in 346. What is arithmetic anymore? Like I don't know what that means. Yeah. Okay, so that would be minus 1. So true. Why do you think I was asking you guys questions? I can't bother with it. Okay, so now if my A is 1, my B is 2, so that would be 3 over 3, so that would be 1. And here, if this is 1, that is 2, that's 1 minus 10, which is minus 9, plus 9, so that's 0. So in other words, I can write the vector 1, 2, 3 as minus 1 times the first vector, plus 1 times the second vector, plus 0 times the third vector. And the fact that I can do that for literally any vector is what makes it span. If you give me a vector, I just plug in the components into this formula, and I can tell you this is the linear combination to get that vector. I could not do that with this. So this one ends up spanning. This means that S2 spans R3. Right? Meaning any vector in R3, I can write it as a linear combination of these vectors using that as the coefficients of the vector. C. So in S3, we only had two vectors to consider. We had 1, 0, minus 1, and we had 0, 3, 1. So this leads to the system of equations, this guy. I performed row reductions to find the reduced or echelon form so that I can find the solution, and it ended up being 1, 0, 0, 1, 0, 0, 0. And this was b minus 3c all over 3. And this guy was b over 3. Okay, so what can we say there? Well, the last row, it's not an inconsistent system. In fact, this has infinitely many solutions. Okay, but does it give us what we want? Think about that. Does that span R3?
I don't think so.
Well, why not? Because what I'm saying is, if I take the vector A, B, C, can I express that as A1 times this guy plus A2 times that guy? Is that solvable?
I could come up with an example of a vector that I don't think we
Okay, what is it?
can. 0, 2, 2.
0, comma 2, comma 2. So you see that there's something going on with the first one? Okay, now what would that say we should do here? This here is going to be my A, this here would be my B, this here would be my C, right? So now can I actually do that? If I write 1,
The A
0,
doesn't
minus-
matter.
What would be the coefficient of this guy? That would be a 2 minus 6, which is minus 4. Right? So it's minus 4/3. What, and this guy would be 2/3. Does that actually work?
It's not, the A is not 0.
So that would give us what? That would give us minus 4/3. And we're already realize that doesn't work. Right? I'll leave you guys to think about it. In fact, this is always true. I mean, I want to come back to this after I talk about linear independence and things, but like that, but you can notice that this will always be true. If S is equal to V1 up to VR, and my R is less than N, then S can never span Rn. This is something that's true in general. It'll be easier to see when we cover a few more things, but basically what this is saying is that if I have two vectors, any linear combination of those two vectors would create what? This is a little bit Calc 3 here. It would create a plane, right? If I have a two-dimensional, if I take a linear combination of two vectors, right? That's like me taking two vectors, this and this, and I take all possible multiples of them. They would stretch out, right, and form a plane, right? Which means a linear combination of two vectors can create at most a two-dimensional space. It will never be able to create a three-dimensional space. So there will always be like one component that's going to mess up. There's going to be a component that we can't achieve. Right?
Is that because the vectors themselves tend to be three-dimensional? Like, assuming that the vectors themselves are three-dimensional?
No, you can make this even a more general statement. If the vector space we're looking at has a certain dimension, say n, then I need at least n vectors to span that vector space. Meaning if you give me less than n vectors, in whatever context, it will never be able to span a vector space that has more dimensions than the number of vectors you're given. And the idea is basically because when you throw it in a system, you will have less leading ones than the number of components that you need to achieve. Right? You can have at most two leading ones here. So there are really only two dimensions that you can really know what's going on. The third dimension is a mystery, and it's going to mess things up. There's a bigger argument here, but it'll be better if I get to the stuff I want to get to. I mean, even though I skipped this part, it's taking a lot longer than I intended. Let's see. So we did that example. I also told you about the null space already. Oh, so by the way, this kind of shows that here's an important thing. Another thing this example shows. Is that, and this will be important later as well, is that spanning sets are not unique. We know, for example, that I, J, and K span R3. Right? In fact, it's very easy to write any vector as a linear combination of those. You literally just take the components and put it in front of them. Right? That's why it's called the standard way to do it, because that's literally the most natural way to do it. But also, we just showed that S2 spans R3. And this is true in any, this is true, this is also, we can also, this is true in general. Right? Any vector space will have multiple spanning sets, in fact, infinitely many multiple spanning sets. So you can think of R2. You'll notice that the way we kind of set things up in math was kind of going by this idea of a standard basis. We can think of I as the vector that runs along the x-axis and j as the vector that runs along the y-axis. But there's no reason why I had to set up the axis that way. That's just something I put on R2. But technically I could have created an axis that were shifted, right? created by this vector and that vector, and I would still cover all of R2 with those two vectors, right? The fact that I do it with a horizontal vector and a vertical vector is just for convenience, right? I could literally take some other two vectors. In fact, I think I looked at, I wrote down an example for this one as well. So I can think of this guy as being the span. So I can say R2 is the span of this. I can say R2 equals the span of I and j. But it's also true, for example, that R2 is also going to be the span. And I wrote down two examples here, 1, 1, minus 1, 2. In other words, I can create the vector minus 1, comma 2, and the vector 1, comma 1. And if I take all linear combinations of that, I will cover all of R2 as well. Right? Now the consequences of this are many. We won't talk about them all right now, but for example, you might remember from Calculus 2 when you did something like a rotation of axes, and certain substitutions in integration is really used on this idea. Right, there was, back in like Calc 2, you were learned about things that can be deformed, and you can have like an ellipse that's kind of slanted, and its equation would not look like an ellipse. You wouldn't really recognize it as an ellipse by looking at it. It's just this random conic section. But then you could kind of rotate your axes so that according to this new pair of axes, that equation of this guy will be an equation that's familiar to you. What you were kind of doing was you were changing the basis vectors, they called it. Right? So you kind of rotate to a more appropriate coordinate system to fit the situation that you can have. And why that is possible is because there are multiple ways to span a set. Right? If looking at my universe according to these vectors don't work, pick two other vectors that are more convenient. Oh, now things work out. Right? And then there are ways where you can actually compute what vectors would be appropriate. For example, in the rotation situation. So spanning sets are not unique. So I know this is the standard, but it's called the standard for a reason. There are other ways to span R2. What else do we want to talk about? I really want, that idea is a very important idea. I really want to get up to that quickly. But that will actually take us into the next section where we can talk about a lot more things. 4 points. We're going to talk about linear independence. So something beautiful happens when you consider span and linear independence together. Let's talk about some definitions here. The set S equals V1 all the way up to Vn is called a linearly independent set if no vector in S can be written as a linear combination of the other vectors. Right, so that's the definition. If I can pick a vector and I can write as a linear combination of the other vectors, I say it's not. Right, so if S is not linearly independent, it is called pretty much the opposite, linearly dependent. theorem. Does anyone kind of see why this is something we might care about? Yeah?
I feel like if you can make vectors in S out of other vectors in S, then it has some extra information.
Exactly. This is a way to talk about redundancies, right? If I can take one vector and really just create it by all the other vectors, why did I need that vector in the first place, right? If I ever needed it, I could have just created it with the other guys, right? It's a way to really slim things down by redundancy. So I can say, for example, I know the set 1, 0, 0, 0, 1, 0, 0, 0, 1 spans R3. If you give me a set of 4 vectors, and you tell me, oh, that also spans R3, sure, but why do we need this guy again? Because I could really just create him from the guys I already have. If these already span R3, why would I need an extra guy in the spanning set? That's just extra information that I don't need. This guy is redundant in terms of the spanning abilities of the set before, right? So if I can create a vector with the other vectors, why do I need that vector? Right? It's extra information because now we're talking about creating vector spaces. Like this guy will be in the vector space created by those guys. I really don't need him, right? So in the case where the vectors that you have are really the smallest amount, the amount you need and no more, that's called linearly independent, right? There's no extra information. There's no redundancies, right? And anything in which that has redundancies, we call it dependent. And there's a theorem for how, I mean, that definition might be a little bit fuzzy, but there's a theorem for specifically how we know when something's linearly independent. S equals V1 to Vn is linearly independent if and only if the equation C1V1 plus C2V2 plus CNVN equals the 0 vector only has the trivial solution for C1, C2, C3, i.e. C1 equals C2 equals C3 equals Cn equals 0 is the only solution. Now it turns out that condition forces you into this situation, right? If I make sure that the only solution to this is all the coefficients have to be 0, then it will also be true that no vector can be written as a linear combination of the others. Right? So let's do a proof. Suppose there is a non-trivial solution. Right? Say, non-trivial would mean one of these guys isn't 0. Say C1 is not 0 without loss of generality, right? Meaning it could be any one of the guys, the proof would be similar. Then we can write, if C1 is not 0, what I can do is I can subtract all these guys, move to the other side. Minus C2 V2 minus minus Cn Vn. And here I would have V1 C1. But the idea is C1 is not 0. I can just divide by it. divide everyone by C1 and call them a new number, say A1 or A2. Plus this here will be AN. And I'd be able to write this one as a linear combination of those. Right? Now, if only the trivial solution. Exists, then we cannot solve for any vector in this way. There are a bunch of ways you can see that. I mean, I didn't actually show you the full proof. You could do it by a proof by contrapositive. You could also show that by our theorems on vector spaces, I would only have 0 equals 0, in which case no information can be obtained. I think we're out of time. We'll stop there for now. We'll talk more about linear independence next time, give some examples, and then we'll combine that with span, and we'll talk about a set that spans something else, and all the vectors are linearly independent, and that actually means something pretty cool. So we'll stop.